Okay. Helen, can you speak again? Let me see.
Hello.
Okay, I hear you. Something wrong today. Okay, let's get started. Hmm. Last time we get started for the tree theory and we go through the basic tree. So the basic tree talk about the basic tree property. Okay, so last time we covered the passing tree and basic tree traversal, this portion. Okay, so talking about what is a tree. Trees, the main issue is it actually is a graph, but a cyclic, not cycle. Okay, no cycle. And then that actually is a tree definition. And then we talk about passing tree. Passing tree is that we do have a equation A plus B times C being passed into a tree of star, and then plus, and then A, B, and the C. This is the passing tree. Okay. So that's actually what we actually covered last time. And today we will not cover this priority. We'll go into this searching tree to finish the searching tree. And then we will cover the priority tree next time for the heap and AVA tree later. Okay, these are the two topics we will cover later. But today we'll be focused on the searching tree. Okay, now let's go back to the topic of the let's go back to the topic of the searching and sorting again. So go back to the searching and sorting. So if you have a linear structure, you search through it, it takes order of n. Okay. If you sorting it, a linear structure sorting it, it will be order of n squared. And then with good algorithm, you may improve it up to order n log n. Okay, this is the basic searching and sorting algorithm complexity. Okay, so these actually in the performance are not very acceptable. Okay, so we want to improve the searching time and the sorting time, right? So if we don't want to touch sorting, we just want to improve the searching part, then you may want to use the hash table or hash memory. So with the hash table, we actually drop the operation down to order of one, and the data being hashed to a hash table. So certain location you hash to a hash table, and then you put the data there. Okay, if there's a collision, you may put it into a linked list, or you can do double hashing. Okay, anyway, there are several methods, but optimal performance for the hash table, the searching time would be order of one. But there is one major problem with the hash table. Okay, the problem with hash table. So Helen, what's the problem with hash table?
Um, that it like takes up a lot of space.
Yeah, because you may hash to some location, but there are a lot of location they are west, and there's a loading factor problem. So loading factor, if your loading factor greater than one half, then your chance to have collision would be increasing bigger. And it's very difficult to manage that the hash table to be well balanced. So this hash table do have some convenience because it give you the convenience, but it do give you some other problem as well. Okay. Okay, so this one is searching and sorting on the hash map, a hash table. Now, later, let's actually look at the other design. So on the same thing, you do sorting and sorting. You may have binary search. So binary search, your performance go down to log n. Okay, that's good. But binary search you need sorting first. And the sorting you need to pay the cost of order n log n. So that actually already burn some time, but you actually sorting the data into a linear structure. So it can be an array or array list. Okay, that's actually binary search on array or array list. Okay. And then sorting, you use a merge sort or maybe a quick sort. And you actually need to spend all the performance of order n log n base case. Okay, that's the performance you have. But you remain on the linear structure. Okay. And then today we would like to talk about the binary search tree. Binary search tree is that we don't store the data into the linear structure. Instead, we send them into a tree. Okay, into a tree. So when we add the data to a tree, then how much time needed to add an item into the tree? So if you add an item into a linear structure, it's actually order n because you need to add the data there and then you need to copy and paste somewhere else. So if we have a binary tree and then we try to build the data into the binary search tree, the performance of the binary search tree when you add the data, it will have a performance of log n time only. When you search for the data, it's also a log n time. So basically, adding the data to binary search tree and adding the data into searching data in the binary search tree also log n. So log n the same as binary search, but in terms of insertion, it will be cheaper. Is that okay? Hi, Sherry, is that okay? I did not hear you.
Yeah.
Yeah? How about Sarah? Are you okay?
Yeah.
So this purpose of the binary search tree is to try to build a data structure that actually can be searching time of log n and also insertion time of log n as well. Okay, and compared to the sorting cost for the arrays kind of the searching that actually binary for binary search you need to do log n performance for the insertion for the sorting and then log n for search time. So this one do have some advantage. Okay, so with that said, today we are going to introduce this kind of a tree that's called binary search tree. So binary search tree, the whole goal is that if you maintain the tree to be binary enough, the overall searching time, the depth of the search tree would be log n time. Okay, in terms of number of elements in the tree. And before we go into that, let's look at another thing. Let's look at Java collections. So Java collections is the collections for Java. Okay, I think this chart I show you many times before. Let's pick a good one. Let's pick this one. So Java do give people this type of the things, okay? But here, remember, you do have queue, priority queue, array queue. So basically, Java's data structure usually is array list is a list made of array. Okay. So now right here, we do see something new that we would like to introduce right now is actually is tree map and tree set. So this is a tree map is a map building on tree. Tree set is a set building on tree. Okay, so the names convention in Java collection is always the same. Here we just want to show you this new two things that we never teach you before in Java. Okay. Of course, today we are teaching you C double plus, and we will build a tree. So C double plus purpose is to build a tree from scratch. You build your own tree, but you need to know that in Java we do have all have this kind of a tree map and tree set you can use. And adding the new element to the tree map is order of log n time. Adding actually searching on the tree map is also order of log n time. It's slower compared to hash map, but in terms of insertion, it actually is better, and then saving the spaces as well. Hash map, we waste the memory. Okay, so that's actually a trade-off between memory and searching efficiency. So basically, before you use it, you need to know about your nature of your problem. Is that more suitable for hash map, or is it more suitable with the tree map? Okay. So let's continue. So basically, today we are going to talk about this kind of the binary search tree. Okay, so binary search tree, tree map and tree set are two kind of abstract data type. Okay, ADT, and then it's a map. It performs as a map, but it's built as a tree. Okay, and this kind of tree we call it binary search tree. So binary search tree, you can call it data structure. The data structure is built as a binary search tree, but the ADT is a map. Abstract data type is essentially a map. Okay, that's called ADT. Okay, so actually we actually discussed the binary search on vector and hash table. We talked about that before. Okay, but here we are actually introducing the tree to do the similar thing. Okay, so basically the search tree operation, you do have map, put, get, delete, length, this different function. Okay, this tree map is you create a tree map TM. Okay, let's assume this is actually of integer in Java. It will be equals to new tree map of integer. Okay, something like that. And then because this one you can use instead of using tree map, you can also use a map. Okay, you can also use map. Okay, and then that will create this is actually the interface. Okay, so you can use that to create that. This is in Java. Okay, right hand side, this is in Java, but here we're talking about C double plus. So C double plus, this searching tree should have all of these to support the operations. Okay. Okay, so we are going to talk about the implementation. So basically, binary search tree, usually you have a number, first number coming in 70. Bigger one, you throw into the right side. Smaller one, you throw into the left side. Okay. So something like that. It's very simple. You build a binary tree. So know that you have that, okay, so you actually get the data and insert it one by one, okay, so you will build up the tree. So this is tree, first you need to have the tree node, okay, and you have the root for the binary tree, and then you gradually insert the data there. So let's look at the listing number one. So listing number one is a tree node. A tree node is that you have a variable called root, okay, and this root is pointer. So the pointer point to a tree node, okay, and then you also keep track of the size. Okay, and initially your tree node is null, size is 0, length is this is size. Okay, so this one easy, we actually okay for it. So then you actually need to look at the tree node. So your tree node look like this. Okay, your tree node look like this. You'd have a key value. Key value is your say your key and the value. So you use the key to compare if there's a match. And the value is your payload. Okay, so key versus value. So sometimes you only have a key, but no value. No value, then you basically is a set. If you only have a key, okay. So here you have key and the value. Value is a payload, okay. So that actually is a key and value pair. And then you have your left child, right child, and they also have a parent pointer. So this one you do have left child, right child, and then you also have a parent's pointer. So this parent pointer actually help in terms of when you need to trace back. When you need to trace back, then this parent pointer will help. Okay. Any questions so far?
No.
No. Then you have a constructor that you set up the value of the key value, left child, right child, and parent. Okay, this is actually the constructor for it. So you can write a easier constructor, okay, fewer parameter, that's no problem. And then you have a has left child checker, have right child checker, and then is left child checker, is right child checker to check if you got a data. Okay, check this one is to check that you have a left child or right child. And then this one, if left child and if right child is that checking yourself is a left child or your parent or right child or your parent. Okay. So this one is the checkers. And then you check if current node is a root or not. Okay. And then check if this one is a deep or not. Okay, root, I think root means this. If you are a this kind of node, you call it a root, but okay, anyway. Deep means you are this kind of a node, okay. And then have any children, have both children, okay, these are the two things. And then there's another function called replace node data. So replace node data, you actually is kind of set node data, okay, the kind of set node data. So you have a key and value and the left child and right child, you can actually update your data. Okay, so this is to replace node data. Okay, this one is set node. Okay, set node. Okay, so far any question? This actually is a tree node and also the binary search tree. Any questions so far? No?
No.
Okay, then next one is to see the binary search. So you need to implement the put function. So put function, you have two put function. One is put, one is underline put. Okay. Right here, one thing we would like to say, what is this underline put and this put? What is the difference between these two functions? Usually, when you put a function with the underline, what's the purpose of doing this? Anyone know? Okay. Usually this underline means it's private or protected. Okay. Private or protected. Double underline is actually is private. So underline may be a private function. So you have put function, you put your key and the value, and then you check if this root, okay, if this root, then you put a key and the value and this root. Okay, so this one you have key value and the current node. Okay, so you put into this. I think this is the current searching tree. Okay. So you're starting from your root to create, okay? So if you don't have the root, so now means that you actually right now your whole tree is empty. Your whole tree is empty, then you create a new node and put the key and value there, and then you do set up the size and then set your root to be that node. So at this moment, if you are empty tree, you will create a new node and then pointing your root to here and set the size to be size plus one. Okay, if you're not, you go to call this underline put. So this underline put is a private function, but actually it is recursive. So this one we have a recursive version and non-recursive version. Recursive version actually will call non-recursive version will call a recursive version. So this recursive version, in fact, is a helper function, okay? Some kind of helper function. This put function is a regular function. So you put the key and value there. That's the only thing that you need to know. But if you are starting from the beginning, you do have a root, then you will search the root node, start to do a recursive call there. So you go to the root node and then you come to here. If the key value less than current node's the key, then you need to add it to the left side. So you check if there is a left side. If there is a left side, then you put it on the left side node. If not, you create a new node and then put it on the left side child. Any questions so far?
No.
So if there's, okay, if actually the key is greater or equal to the key, you put on the right-hand side. Put it on the right-hand side, it will be this side. And then you recursively put it there. Or if there's no right child for the current node, then you put the new tree node to the right side child. Is that okay so far?
Yeah.
Any question?
No.
So this one not too hard, okay? This building of the tree not too hard. So that is your put function. Okay, now next one, let's look at the get function. So the get function, you would just try the key. So you search your current key, and the current root node. Okay. Okay, if there is some node being found, then you return the payload value. If not, you return 0. Okay, 0 means null. Okay, actually it means null. Okay, and then if there's no root node, you also return null. So basically, this one show you how to do the get. Now, next one, you also do the recursive version with the underline. So the recursive version is the current node. You go into there and you check. If the value is equal, you return the current node. Otherwise, you check the left node. Less than, you check the left node. If not, you go to the right node. Okay, so that this is recursive version. So remember the get function and the underlying get function. Get function is a regular version. Underlying get function is a helper function. Okay, this one will go into searching. Okay, this one is listing 6, and then we go to listing 7, delete. Okay, now this one's delete. Delete first one, you need to basically get it. You get the current node. So you get that node, and then what you would do is that you do have this search for identifying. Let's assume that this is the node that you want to delete. Okay. And then you do have your own left child and right child, right? So basically, you want to delete this node. So if you have both left child and right child, you will promote one to here. Let's assume that they compare, maybe smaller, maybe bigger one. You compare and then promote it to this node. So basically, what you would do, let's assume that you promote the right child. Okay, you promote the right child. You promote the right child after the delete. The parents will go to here, and then this one's left child go to here. Okay. Other than that, there's nothing changed. You just need to do that. Okay. So basically, let's look at the real operation. So you look at the key. So you if this is size greater than 1, okay, then you actually the key value greater than 1 is the root. Okay, 1 is the root. So the size greater than 1, and then you will need to delete. Okay, so you actually will get node from the root. Okay, and then you got the node to need to be removed, and then you do remove the node to be removed. Okay, then size is decreased by 1. If you found the node, if not, you will return key not in the tree. Okay, you will raise a exception and then do that. Okay, if your size equal to 1, that means that your root node is the only node you will want to check. And the root also equal the key, then your root equals null, and then size decrease by 1. So this one is in case that you have only one node. And then the rest of them is you do not find, or the root is not what you want. So basically, this is still not too hard. Any questions so far?
No.
So the real remove operation is in the remove function. The remove function will basically do the operation of this is the one you want to remove. You need to promote one node and then pointer changes. Okay, pointer changes. So let's see. This one is to check is a deep node or not. Okay, this one easy. Check the deep node or not. This in 10, I think that if not a deep node, if not a deep node, then it at least has one child. So checking the left child and right child. Okay. So this left child and right child is to do operation on it. Okay, to do the operation to modify your pointers to replace data. Okay. And then there's a function called find successor. Find successor, I think this function is during your searching, you kind of go through here and then successor, next one, the next node you actually will go to. That actually is called your successor. Okay. Okay. And you successor is called the find minimum. Okay. And then there's a splice out function. Okay, let me try to bring up this binary search code. Okay. Okay, so this file I think is the program for binary search tree. So you do have a tree node, key value, and payload. Okay, as a string that we want to have. And then we have a tree node constructor, has right child, has left child, is left child, and right child is root, is lived, has any children, has both children. Okay, splice out function. Okay, splice out function is remove the node from the tree. Okay, this one is the purpose is remove a certain node from the tree. And then find successor, you use the property of binary search tree called the in-order traversal to print out a node in the tree from smallest to largest. So this one is to recursively finding the tree's traversal from small to the largest one. So you visit your left side first and go in the middle. It's an in-order traversal for the tree. So that's not hard. Okay, this one, finding the next successor that you have. Okay, so these are the basic binary tree. We do have this binary tree in a whole program. Okay, this one is a binary tree. So let's look at the main function. Okay, so there is a BST part. Binary search tree. So there's a BAT bet. Okay, so BSTH is the main function. Let's look at its main function. Okay, the main function right here, you actually create a binary tree, and then you put 3, okay, 4 and 6 and 2, and you try to get them. Okay, you try to get them. Okay, so this one is a function, and the B1 is a BAT file. You will compile it and then go into a tester function. Okay, let's do it. Okay, so you do get the result that you should have. Okay, so this BAT function is a function. So this type of the tree, I think is actually usually happen when you are trying to build a large file system or searching tree system. Okay. You do need to choose your key and the value to search. And then in competition or LeetCode usually not going to test you the whole binary search tree because I don't think that anybody can finish it within the time, okay, within the time. So let me give you the code and then let me give you the coding. Okay, give you this bst.cpp function, okay? Because this kind of data structure, usually when you need the operation, you search it for the internet and then get a version nowadays because usually we just need to do that, okay? So this one, the algorithm is not too hard. You just need to know about the basic operation of it, okay? Okay, so that's that. This one is the topic of the binary tree. So let's look at the tree analysis. So the tree analysis is to look at its performance factors. So worst case, you may have these. So your searching time and the insert time will be order of n. That's the worst case, okay? You are very unlucky and your data actually is totally out of order, then you may have this worst case performance. On the average, actually log n, a base case is log n performance. So worst case for it is actually order of n. Okay, let's see, the order of n. Okay. Okay, anyway, this is the topic of binary search. Not too hard, okay? Not too hard. Going back, okay, so this one we finish it. Next one, let's look at binary heap, okay? Let's look at this heap part. Okay. This heap part, actually, we do talk about it in what? In the Java part. So binary heap, we actually build a binary tree in the linear array. But when we build a linear array, we actually on purposely put one and then two child. Okay, the two child is actually 2 and 3, and then two child for the 2, and then two child for the 3. That will be 4, 5, and the 6, 7. Okay, we do this kind of data structure, and then we can implement a binary tree in the so-called linear structure. Okay, so this actually is one kind of the trade-off. Okay, so let's see. No. Let's look at the slides here. Okay, so let's get started. Priority queue is binary tree. So priority queue with binary tree is that you keep the order of the like a queue, okay, but you build with a binary heap. So this one, the largest one is right here, and you have two value here. two smaller one on 2 and 3, okay? So with that, you will build a binary tree heap. And inserting the vector is order n, sorting is n log n, okay? And then your inq and dq is order or log n both. Okay, it's order log n. So basically this one, because you have the one, this is maximum. And then you have a two value right here. This one will be the maximum for this side and maximum for this side. If we are talking about a max heap. Okay, so when you insert, usually you just insert right here. But if you actually would put into the new node location right here, okay, you just put it here. And then you promote the right, as you compare with its parent, if it's bigger, you will move up to swap between the parent and itself. Okay, that's the idea. So basically, the insertion is order of log n. Since you put into the new location and you keep swapping, the worst case will swap until you actually replace the maximum. So actually it will be log n time for it. Okay. So basically, when you only have one data, you actually just the data, and you have put a 10. You put a 10 over here. This one is a min heap. Okay, min heap, you keep the minimum on top. So if you have another number come in, you compare with the parent, you don't change. Next one, you have an 8 coming in, you will actually swap an 8 and 10. You swap yourself and your parent. Okay. So the calculation of your parent ages and your right child and left child ages is very important. The indexing is very important. Okay, there is a special function to calculate the left child and right child. Okay. Okay, so here we do have a binary heap constructor. Insert function find minimum, delete minimum is empty, and this different thing. Okay. So there is a function. Let's actually get this one. Let's copy the whole thing, okay? Let's just copy the whole thing. Okay. And then right here, let's actually create a new directory. Let me put it into here. This let's create it a chapter 2. Okay, the heap. Okay, right here, let me create a new file that's called min heap. Okay, this one, let's look at it. It's a binary heap, so bin heap, okay? But here it maybe is a min heap. Min heap means minimum heap. So heap has a max heap, min heap, okay? And this kind of heap actually, in terms of interview testing, is more likely to be tested than the binary search tree, okay? Then you do create a heap vector, okay? Your heap vector is your linear structure for the priority queue. Okay, and then you have the current size. So initially, you actually you can load it a vector to it, okay? And then you change the size, okay? And then there's a push up. Let's don't look at push up first. Let's look at the push up, push down, mean child, delete mean, PO heap. Okay, it's empty. Check in if it is empty. And then find minimum is the vectors of first element. This have no problem. Okay, this have no problem. Now that's next one. Let's look at the insert function. So when you do insert, you put it at the last element. Okay. This last element means that you actually already have many nodes. And this last element will be the one that you actually to be inserted location. The last element already be that. So this one has no problem. Okay. So your size increase. And the next thing you would want to do purse up. Purse up it means that you would compare with your parent. If it's okay, you continue to move up. Okay. So let's look at the current purse up function. So purse up function while I divided by 2 greater than 0. So this one is 1. This one is 0. This one index is 1 and 2. This one index is 3 and 4. So if your current node is I, then this one is 2i plus 1. This one is 2i plus 2. Okay. And then your right side 2 pointing to 5 and 6. The left child is also 2i plus 1. Left child is also left child is 2i plus 1. Right child is 2i plus 2. Okay. So basically, your left child number is 2i plus 1. Right child number will be 2i plus 2. Your parents node, maybe you are this one, maybe you are this one. Your parents node would be, let's assume this number is I. Your parents number would be I minus 1 divided by 2. Okay, so this one is 5 minus 1 is 4, divided by 2 is 2. 6 minus 1 is 5, divided by 2, you will get 2 as well. So this is your parent node's number. Okay. Any questions so far? This priority tree, the only thing that you need to remember is this how to calculate the parent node's index number. Okay. Any questions so far? Okay, this part of the code actually usually the performance is the main idea. Okay, you need to keep track of it. Okay. Okay, so you basically you want to purse up, so you actually compare current node and the parent. I think they are using 1, 2, 3 system. Okay. They are not your root node is actually 1, not using 0. So if it's using 1, your left child is 2i, right child is 2i plus 1. Okay. And your parent should be half of your I. Okay. This actually, if you using this, that's actually a little bit easier. Okay, anyway, so let's see. So you compare your current node and your parent. If you are smaller, then you do swap. This is swap algorithm. And you set your, try to find your parent node. Okay, so this one is your purse up function. Any question?
No.
Okay. So that's the insertion. Let's look at the deletion, okay? So delete the minimum, you actually need to basically you will have a tree. So you remove the top left one, you remove this one, and then you should take the data from the last element and put it on the maximum. Let's see. And then you do purse down. Okay, you do purse down. Okay, you do compare to purse down. So basically, this one is when you do deletion of your top one, you actually get that value, and then you actually need to promote a node. Okay, promote a node. You get the data from what? From your current size. Okay, current size is the location you do that, and then you reduce to the size, and then you pop out, you delete the last node. Okay, last node. You actually put it on the top, and then you push down from the number one. Okay. So let's look at the push down from number one. So push down number one from number one means that you are in number one, and every time you compare your 2i, okay, less than the current size, then you will find the minimum child of the I. So you compare your right child and left child, and then you find the minimum one, okay, and the minimum one compare with your current node. If the minimum child is smaller, then you do swap, okay. You do swap, and then you purge down, continue to purge down your minimum child. So basically, it's like this. Let's assume we have let's assume that we do have a tree of 1, 2, 3, 4, 5. Okay, let's assume that the tree is like this. So you kind of remove this one. So you will return this one. So you put your 5 over here, and then you compare the minimum. Minimum is 2, so you do swap between 5 and 2. Okay, so your 5 go to your minimum child, and your minimum child continue to compare with the minimum child, and then you do swap. Then this will be done. Okay, so basically this one has a purge down that would do continue of the purge down function. Okay. Okay, minimum child just compare your right child and left child. Okay, that's it. And maybe sometimes you don't have right child, don't have left child. That's it. So basically, this is how it works. Okay. So this kind of the min heap will maintain the order of the data. Okay. The first one is always a smaller. So it is used as a priority queue. It is used as a priority queue. Okay. So min heap or max heap usually use of the priority queue. Performance-wise, let's look at performance-wise. Okay, now there's no performance. Performance-wise, it actually usually finding the minimum. The minimum is only order of 1. Okay, and if you consider the push down part, it will be log-n operation. Okay, insertion is also log-n operation. Any questions so far?
No.
No? I think this part is easy, okay? We just don't waste our time. Let me give you the code as well. Okay, let's move on to the next one. Next one, let's look at the balance tree. Okay, balance tree, this one, the topic is more difficult. And there apparently your tree may be unbalanced because you keep putting the whole thing to the right, okay? So it's possible that you sort your data first, and then you pick the middle one to insert it into the binary tree, and then slowly do binary searching to build up your tree. In that case, you need to pay up front n log n sorting fee. Okay, that's one way you build up your balanced binary tree. So this is a balanced tree right here in this chapter in the book. Right here, actually, it's talking about next one. We're going to talk about binary searching tree, balanced searching tree, and also AVL tree. Okay, and then the tree will finish the tree topic. Okay, tree is not hard. Graph and the dynamic programming is more difficult. Okay. So let's assume that let's actually go into here. So basically you would have a search tree operation. And then you need to keep it balanced. Okay. So you need to study the balanced binary tree. Okay. So a tree is a graph of the node, age and child node. Okay. And it's acyclic. And usually is used for file systems. Okay. So binary tree, binary search tree, we talked about this already. Okay. Searching time, we talked about it. Now, next one is actually in the previous section, we look into building the binary search tree. As we learn, the performance binary tree can be order of n if it's a worst case. Okay. If it's unbalanced, if it's balanced, it will be order log n. Okay. So there will be a tree called AVL tree to keep it balanced. So there is a balance factor. Balance factor is the left-hand side tree height compared with right-hand side tree height. So tree height is talking about the depth of your tree is called tree height. Okay, how many level you have is tree height. So you actually try to measure your right child tree depth and left child tree depth. So the difference, we call it balance factor. So balance factor equals 0, that would be the best balanced tree. Okay. So that's the only thing you need to know on the here. Okay. So you need to keep your balance factor low. So this one, let's see, is unbalanced. So let this know left side, right side depth is 2. Left side depth is 1. Okay. This node left side balance is 1. Right side actually is 3. So it's quite unbalanced. So one way to solve the problem is to insert into binary search in solid order. So in solid order, we pretty much know how to build it well balanced. Okay, well balanced. So that's one way that I talk about can solve the problem. Okay, so a balanced tree have enforced the height with n node is close to log 2n. In other words, the size of the left tree is roughly the same as the size of the right child. Okay. A balanced binary search tree underline the implementation of the set and map. Okay, you see that in fact the set and map using for C++ is using tree map. Okay, they are using tree map. They are not using the hash memory. So here you do have print, contain function, insert function. Okay, this different function. So this one is your binary search tree. you have binary search tree. Okay, this one actually including the content function, insert function. Okay, insert and insert function. Okay. Okay, it's BSH. Okay, let's look at this one. Binary search tree and the main function. Okay, let's look at the code. Okay. I think it's not this one. Okay, I'm not sure where it is. Okay, let me check. Okay, let's do this. Okay. Since there are several codes, let's do this. This one is bst.h. Okay, I think this one is actually can be used. So let's create a file called bst.h. Let me copy it in. Okay. I'm not sure where it is right now. So let's copy it. Okay. So this one, let's remove the unwanted character. Okay. Now let's copy the second half in. So there's a content function. So this content function is the part of this BST, okay? Okay, that content function. Now this one, let's go to this one, insert function. Right here, a little bit dark. Okay, let's copy up to here. Okay. Okay, let's copy this part first. This part is the main function, okay? So this one's the main.cpp. Let's copy the main.cpp first. So here it has the main.cpp. So this main function basically include bst.h, and then there is a creating the binary search tree, and then the binary search tree we do insert the print, okay, and then checking content function. Okay, so this one is the main function, but the bst.h right here, it is a BST tree, and then there is a node structure. Okay, the node itself had a constructor, content function, insert function up to here. So I believe that up to here is actually up to here. I think this one, this is the node structure. Okay, this one up to here. This one is the node structure up to here. Up to here is node structure. Okay, and your root itself is a node. And then you have a binary search tree. Your binary search tree is built upon using this node. So let's actually reorganize it a little bit. This is a little bit too complicated now. So let's actually create another one. Let's call it node.h. Okay, let's actually modify it a little bit. So let's do include. Okay, no. If undefined node underline h. Okay, then define if undefined, then define node h, and then if, okay? And then let's move the node definition to it, okay? Don't keep that in the BST. It's actually a little bit too complicated. So let's cut and paste for this insertion up to here. Put it in the node. Okay, so this one just for node. So the node, that's actually right here. That's actually, it will also need to have the type definition here. Okay, so this one need to have a type statement. So this node is the node of the type value, T type value, okay? And then there is left child and right child. And then you have the value, left child, right child. You have the print function, you have content function, you have insert function. Okay, that's it. This is one is your node. So node by itself had no problem. Now let's multiply our PST. So PST will include this, and then it will include node the H. Okay, you include node H, so then you would have your binary search tree. And then let's delete the node definition. Everything related to node, let's delete it. Okay, then it will be more clear. So basically, you should have your private section right here. That's actually called a root. Okay, let's actually also delete this insert. Maybe we don't need it. So you will have a private section that come with node. And your binary search, you have a print. Then you recursively calling the print function. There's an insert function, there's a content function. So you will call the print function from the root node, and you have your insert and your content function. Then your PST is done like this. Let me check if there's any more error. So end of this, and then you have your content. Let's see. Let's read it. Okay. You contain the value. If your root is null pointer, you return false. Otherwise, you return your root node's content value. Okay, recursively calling it. So this one, okay. You insert value, you have a value. You check the root is this one. You will put it in the new node and then assign it to root and return true. Otherwise, you'll insert a value using the root node to insert. Okay, that's okay. And this one, okay, let's go to the node as well. So your node would have your print node, your print. Then if your left child is not empty, you go the left side recursive print, okay? And then otherwise, you right side recursive print, okay? And then that's this one, okay. Content, you check a value. You check your current value with your value, okay? If yes, you return true. Otherwise, in the stand, you check your left side. Otherwise, you check your right side. Okay, and then insert the simile. Okay, should be fine. Let's actually save them. So right here, we do have this. Let's do save. Okay, okay, now let's actually try it. Okay, right here, we are going to somehow this is slides. I'm not sure, but this portion is just garbage. Okay, we basically can delete it later if it is really garbage. So now we will do this kind of the compilation. Okay. So let's see, this one is going here. Let's do G double plus dash 4. Then you have your main.cpp dash O test 1. Going back to the node, okay. This one, we need to include this. and then using namespace HTTP. Okay. One more time. This one, a lot of error. Let's see. Missing template argument node for deduction. So it actually missing main function. Actually, let's see, it's in right here. So this one it is node t value. So this one should be coming to this BST. You have a T type. Then this one should be a node T type. Okay. Okay, let's do it one more time. Okay, and then this one. Okay. So I kind of modify the code a little bit, put it into this separate file, and it worked. Okay, and it worked. Any questions so far? So this one give you the node and binary search tree, one more implementation. And then we are going to talk about the balance tree. So this one for sure, this part is an error. Okay, let me clean it. For some reason, it may just copy it there. Okay, so this dealing with the BST application. I think this part is bypass it. Okay, the searching tree algorithm, I think that's fine. So you will go into the unbalanced tree example. Let's look at it now. Okay, go to the case study. So a node, it will be n factorial possible insertion permutation. Okay, that's true. And then it may be balanced, may be unbalanced. So you can calculate the average height of unbalanced binary search tree. Okay, that actually is fine. So this one, they are technique to calculate the mean binary search tree's height. Okay. This one is to look at map and then calculate the average binary search tree's height for the map. Okay, I think this one fine. Okay, let's actually continue. Memorization is sort of application is one of the rule of recursion. Okay, we talk about memorization before. We have the two-way top-down approach called memorization, bottom-up called tabulation. Okay, this part. This one is going to talk about iterator. Iterator is a special class that added to your constructor. So it will traverse to the next node in your tree. So when you do searching or you do serialization, you'll be faster. Okay, that's the whole purpose of having the so-called iterator. So let's look at this one, have a binary search tree, and then using the iterator. Okay, so binary search tree with iterator. Let's look at this one. This one is called binary search tree with iterator. Let's look at this one, okay? So let's look at this one, binary search tree with iterator. Let's create a new one. This one called est with iterator.h. Okay, let's copy it over, okay? Sorry that I cannot find my code anymore, so I don't know where they are. Buried in my hard disk. So this one, let's pause it, okay? Somehow the space key in computer is in the PowerPoint is different from the one used. Okay, up to here. Next one. This one, you would have a template. Okay, sorry, this one quite many space now. It's okay. We'll modify it later. And then page 2, page 3. Let's complete every page before we modify the code. One more page. Number 4, the insert. So this kind of different kind of tree is actually doing the same thing. You do content function, insert, delete. Those different function is always the same. Okay, finish the insert. Let's actually do one more page. This one is operator, curly brace. Okay. The indexing operator. Next one. Okay, next one is class iterator. So let me check, okay? This actually, so far my class finished. Next one is the iterator class. So iterator class is a different class, but in the same file. Okay, that's iterator class. Okay, so this BST file with this BST file with the iterator is quite huge. So this BST underline H, there's one more underline. Okay, there's one more underline here. We are going to clean up this one, but at this moment, let's just keep it like this. Okay, we will clean up. Okay, we will read it and clean up soon. And then that's it. Then there is a main function, and then you do BST underline CPP. Okay. Let's see. There's a main function. Okay, let's look at this code first. So this one is a binary search tree with iterator. So you type define your variable, and then you have a node. Okay, so these different spaces need to be removed. So this one also use the node structure. Let me try to do this, see if I can copy one of these. And then let's use a replacing file. So let's see, this one, let's actually do replacing file. So do this replacing file with a space. And then let's do all of them. Let's see. Do replace all. Okay. So I use a replacer to replace them. Let's see if it actually do faster. Okay, that's good. The replace all work. Let's see, let's look at it. Okay, there are not many error now. Just remove this different kind of character now. Okay. We basically finish this one. Let's look at it. This one have a node, okay? So the node is the same, similar with the previous one. Now create a right node and the left node, and there's a recursive printing function, okay? That's the node, and then contain function, and then insert function for the node. So up to here, it's similar. And there is this portion, let's see. This is node structure, and you also can have a operator, this one is array value, array function, okay? So up to here, I think this one is the node up to here, okay? So this is the definition of your node. Let's see, let's check, okay? The node is going to insert, and then there is a value. So this up to here is a node definition. Then you have the iterator. Iterator is a vector of the node and put in as a step. So when you insert the data, you actually put it into a step. And then when you take out the data, each of the vector value is a pointer to node. So you point to the node and you can find the node faster using the step, okay? So that's the idea. So your constructor initially is empty, and then you actually, and you have create a node, and then operator not equal, okay, you replace that not equal equation. You actually have the operator star value, okay, the body value, okay, the body value, you can find the return the key and pair. It's an increment value for the iterator increment. Okay, so up to here, this one up to here, you have the node definition and iterator definition. Then you have the root, and then you create your binary tree. So your binary tree actually have a root, okay? And there's also a begin function that uses the iterator, now return the iterator case. And then begin will check if the root iterator, okay? End will actually using the iterator to empty to see what value it is, okay? So iterator constructor with no value is this. If iterator with root node, it will actually continue to see its left, okay, and push back the value to the stack, okay. That's the iterator's function. So overall here you have the bracket content, insert, okay, whatever. This good enough. This one is called BST with iterator. Let's look at the wrong code, okay. Let's look at the program that will run it. So let's look at the main function that will run it, okay. The main function will run it. The main function that will run it, let me see. I don't see the main function that can run it. Okay, let's copy this main function to paste. Okay, copy to a main function, change name to main function. With iterator. Okay, let's call this function main function with iterator. So right here, let's call BST with iterator. Okay. So you get your BST definition from the BST with iterator. And then here you actually using the data of the key value pair. You keep the data for key value pair. It's no longer using only the key. So right here, that's actually assuming that the key value is key and value that's used as string. Okay. So that's actually creating include. Okay. String type. So insert, that's insert one. Let's do Arial. Insert two. Let's do Brian. Insert three. Let's do Carol. Okay, so we insert three data into it. Let's do this. Let's do this one as 2. This one as 1. So when you do it, 2 will be here, 1 will be here, and then 3 will be here. Then you do bst.print, you print everything. Okay, recursively print everything, and you finish. And then you try to check this different X to see if it contains the value. So let's check different value. We have 1, 2, 3. So let's try 7, 3, 2, and 4. See if these are in there. Okay. So like that. Let's just save. And let's do it. Let's do G double cross HWALL. And then this one main with iterator the CPP test0 test2. Okay. And last one test2. Okay, so it actually print you the tree structure that we have. Let's make the tree structure a little bit more complicated. Okay, this one so far not as complicated. Let's actually print it. So let's assume that we do have a 4 right here, and then we have 2 right here. Let's have 1 and 3. And then here, let's have this one as a 6 right here. Let's have a 5 right here. Let's here have a 7 right here, okay? And then each one of them, let's assign A, B, C, D, E, F, G to it. Okay. So let's try. So let's try 2 Carol, 3 this. Let's actually copy this one. Okay. And then let's do 7. 7 is G. Let's do Gabriel. Let's do 4. 4 is actually Daniel. Let's do 5. 5 is, let's use Eric. So it's missing 6. Let's actually do one more. BST number 6. This one, let's use F, so blank. Okay, so we have 1, 2, 3, 4, 5, 6, 7 added to a tree, and we are going to check these different scenes. Okay, it's different scene in here. See if the keys contain. Okay, so this one is a binary tree with iterator and also coming with integer and string, the key value pair for the binary search tree. Okay, I'm trying to give you another example for it. This one, different structure. Okay, you see, it actually print out the structure for it. Okay. The binary tree is inserted by the time of arrival, not actually by the number key value. They don't compare the key value. Okay, is it by the time of arrival? It's okay. But the contain or not contain tree actually is correct. Any questions so far?
No.
No? Okay, anyway. Today we go through the binary search tree and then teach you one design that actually has a binary search tree without any property, only key value, okay? And then we also cover the binary search tree with node and with iterator, okay? And this with the iterator, we actually just teach you how to make the for each loop work and how to make sometimes you have the function that require the iterator to work, okay? Then you need to implement the iterator class. And iterator class in your binary search tree, you need to add the begin function, the end function, okay? These are something you need to have. So usually this is how you build a class with iterator and different. So this one is a little bit more complicated in terms of the data structure, okay? But I guarantee you this kind of problem will never happen in the competitive programming, okay? It's usually in the database course or something that contain the bigger systems, okay? It will not happen on the competitive programming because you just need to implement a binary tree that takes 3 hours. Nobody is going to finish it, okay? Okay, any more question? No?
No.
No, that's it for today, okay? See you next time. Bye-bye.
Bye. Thank you.
Bye.
Bye. Thank you.